Students, good morning. Uh, Today we will continue the discussion on total derivatives. In this lecture, we will try out some corollaries and do some numerical examples. So, corollary number one, if z is a function of x and x and y are again functions of u and v, then del del u of z can be written as del del x of z into del del u of x plus del del y of z into del del u of y, and del del v of z is written in the similar way like this. And corollary number two, if u is equal to fxyz, that is a function of three variables, and xyz are again functions of t, then u is a composite function of t, and dgt of u is equal to del del x of u into dx upon dt plus del del y of u upon dy upon dt plus del del z of u into dz upon dt. So this is simply extension of the two variable case. Corollary number three, if fxy is equal to c, that is f is an implicit function, then we know that dy upon dx is equal to minus fx upon fy. Now we are interested in what is the value of d square y upon dx square. So differentiating dy upon dx again, so denominator, derivative of numerator minus numerator, derivative of denominator upon denominator square. So this is, next thing is this. Okay, so now this denominator as it is, but inside here it was fy outside and dx of fx. So this concentrate here, dd of fx. It's again written like the same definition. Okay, that if y is a function of x, then it is ddx of fx plus, sorry, del del x of fx plus del del y of fx into dy upon dx. So from here I get this fxx double derivative of f partially with respect to x, and this is fx derivative of fx with respect to y, so fyx, and dy upon dx is minus fx upon fy. So this expansion is put over here. Okay, and similarly this second part is written like this, and minus and outside, just so simplifying the things. No, just multiply fy here and taking in the fy in the denominator, so this becomes fy cube, and then this becomes this one 2 times this and this upon fy cube. So this is the value of d square y upon dx square, this value. Okay, next thing is a numerical example. 1. If z is a function of x and y, where x is equal to e raised to power u plus e raised to power minus v, and y equal to e raised to power minus u minus e raised to power v, then show that del del u of z minus del del v of z is equal to this. So what to do? We can see from here that z is a composite function of u and v. Okay, z is a function x and y are again functions of u and v. So z is a composite function of u and v. Therefore, we will use the formula for that. So del del u of u, del del u of z can be written as del del x of z into del del u of x plus del del y of z into del del u of y, and then this del del x, del del u of x and del del u of y are obtained like this. So if you concentrate here, so del del u of x means e raised to power u, derivative of e raised to power u with respect to u is e raised to power u, and derivative of e raised to power v is 0. Okay, similarly in the second case it is written, okay, del del u of y from here. So minus of e raised to minus u, and derivative of this is 0. Similar is done for the second case. Okay, so del del v of z, this expansion and this derivative are computed like this. Then what I did simply, I did this del del u of z minus del del v of z. So from here, sorry, yes, here I was here. So I got this and this. Now what is this? This is already given x and this is y. So this is equal to x into del of z minus y into del y of z. Now taking up second question. If u is equal to f y minus z, z minus x, comma x minus y, then prove that this is equal to 0. So in this case, let us assume that capital X is equal to y minus z and capital Y is equal to z minus x, and capital Y is this, capital Z is equal to x minus y. So now what happens? U becomes f capital X, comma capital Y capital Z. Fu is a function of x, y, and z, and x, y, and z are again functions of small x, z, small x, y, z. So therefore this u is a composite function of x, y, and z, and therefore we can use the similar formulae as we have learned earlier. So for example, del x of u is equal to del capital X of u and into del small x of capital X, likewise this. So this way we can write the formula, then we have to find out the values. Now what the value of del x of capital X, that is 0. Del x of capital Y, that is minus 1. No, sorry, yeah, it's minus 1. And del x of z, that is 1. So this way we will be writing these, and then each case for del y of u and del z of u, and then combining all these, and we are going to get this summation is equal to 0. You can try out it. Now going to the next part, that is question number 3, find dy upon dx. So this is implicit function x raised to power y, y raised to power x is equal to c. So again, in order to find out dy upon dx, you have to find out minus fx upon fy. So compute that from here. Okay, consider this small f is equal to x raised to power y plus y raised to power x minus c is equal to 0. Similarly, you consider f is equal to cos x raised to power y minus sin y raised to power x, and then find out del x of f and del y of f, and then put in the formula dy upon dx equal to minus fx upon fy. You get the desired results. Then coming to question number 4, if w equal to fxy and x is equal to r cos theta by r sin theta, then show that this is equal to this, that is del r of w whole square plus 1 upon r square del w of del theta of w whole square is equal to del x of f whole square plus del y of f whole square. Okay, so in order to do it, w is a composite function of r and theta. You can see here w is a function of x and y are again functions of r and theta. So therefore this w is a composite function of r and theta. Again we are using the formula del r of w equal to del x of w into del r of x plus del y of w into del r of y. So yes, now I can find out del r of x as well as del r of y. So these are cos theta and sin theta, and then yes, so I got this one right, because w is f, so I can write f over here. So I got this. Similarly, we can find out del theta of w by this expansion. So del theta of x is minus r sin theta, and del y theta of y is r cos theta. So again this taking this r this side 1 upon r and keeping all other things here. So I got this equation 1 and equation 2, squaring and adding equation 1 and 2 we get. So just squaring this one, okay, a square plus b square plus 2ab, okay. So this is this square, which one, this square, what happened, what was one was this, so yes, del del r of w whole square plus 1 upon r square and del del theta of w whole square, right? This is left hand side, and in the right hand side I am taking things from here. So del del x of f square cos square theta plus second one this square and this square plus 2 times this and this, and then second one here minus, so a minus b whole squares, then this a square plus b square, and a square this one whole square, this sine square theta del y of f whole square cos square theta, and then minus of, so this no plus, not plus but minus of, I was here minus of 2 times this one, okay. So minus of 2 times this one cuts with plus this one, and we are only left with these two terms and these two terms. So from here if we see that this can be common in these two terms, del x of f whole square common, and inside cos square theta plus sin square theta. Similarly this thing common and sin square theta plus cos square theta. So this is, and its value is 1, sin square theta plus cos square theta equal to 1. So I am only left with del x of f whole square plus del y of f whole square. So that's the answer to this question. And